yesterday we talked about the history of the atomic theory. Today we want to talk about the modern atomic theory, what we think nowadays. Okay, of course there were some mistakes even in Dalton's theories. You know, he had some ideas that were a little bit wrong. We now kind of been disproven. And going back thousands of years, there was no real reason to believe that because there was no scientific method. This is our best guess at way the atom looks right now. All right, the modern atomic theory. So get your notes out. We'll take a little bit of. You've probably seen a lot of this stuff already before, I'll bet. Modern atomic theory. Well, you know, some of it stayed the same. The one big thing that stayed the same is that we still believe all matter is composed of atoms. Okay, kind of like Dalton and Democritus way back 2,500 years ago believe. But we don't believe everything that they did. Okay, all matter is composed of atoms. We now kind of know that these atoms are made of smaller particles. Protons, neutrons, and electrons. You've heard of all three of them, I'm sure. We're going to talk about them again. I'm going to give you some notes on them, and you're going to actually use them. A lot of times, you know, you may have heard some of these things before, but kind of like in your middle school days, or even maybe in bio or integrated, you basically only saw a very cursory, short, chemistry section. Then you kind of never saw it again. All right. Well, here we're going to talk about these things, and we're going to use them all year long. I'm going to give you a periodic table this year that you'll be able to use this year. I'm going to give you a periodic table today that you're going to be able to use for the rest of the year. Every single test, you'll need it. If you don't have it, you won't be able to do the test. It's as simple as that. All right. So this is not something you're just going to see once. So I'm going to start with stuff you have heard of before. All right. Now, first off, although we now know it's not true that every single atom is, like probably Democritus thought, or even probably Dalton thought, is different. Like a carbon atom is completely different from a nitrogen atom. It's different, but they contain the same things. It's the arrangement and number of the things that they has, how many protons, neutrons, and electrons, that determines what atom you're talking about. All right? Everybody's made of protons, neutrons, and electrons. There's nothing different from one proton to another proton. There is something different from one carbon atom to an aluminum atom to a hydrogen atom. They are different because each of those atoms has a different number of protons. Okay? So it's the number and arrangement of the particles that determine each atom's unique properties. Why is carbon carbon? Because he has 6 protons. As simple as that. That's why he's carbon. And you'll see that. I talk about it today. Now, I'm going to talk about each particle individually, its properties, and what you guys probably already know about them. Some of it, and some of it you won't know. Some of the things that you don't know. A lot of the stuff you get confused. A lot of the words today are going to be similar. You're going to get a lot of words today that sound alike. By the time I'm done, I'll go over them all. And they actually have a list over on the wall, the little word wall. Just put the new one up vertical there. That's all for this chapter. All those words we're going to go over, you'll notice some of them are very similar. Atomic number, atomic mass, ion, isotope. All those things, you're going to easily get confused, and you do. Okay, so I'll try to make it as clear as I can for you here. All right, let's start with the electron. What is the electron, and what do you already know about it? I bet you know quite a bit about electrons. First of all, what's the charge on an electron? Who remembers? Who knows what a charge is? Raise your hand. Who can remember a charge on an electron? Karen? Negative, yeah. Electrons are negatively charged, -1. They get given the charge. Do you remember where they're located? Remember making models of these maybe in middle school or elementary school? Remember where they're located? Where are they? Outside the nucleus, yeah. They're located outside the nucleus. And what are called energy levels. You probably drew those energy levels back in the day. You probably drew them as rings like this, okay? And, you know, you could use that. It's not a great description of what really happens, but we often use rings to illustrate the energy levels. When we get to the next chapter on the electrons and quantum theory, we're going to learn how inadequate our two-dimensional drawing of rings around the nucleus is. It really isn't what electrons look like, but that's how we usually represent them, at least in a textbook. Okay. What else do we know about electrons? They're located outside the nucleus. You know what? If you remember the Bill Nye video, electrons are responsible for, what do they do? What do they do out there? Ben, what are you going to say?
I was going to say they're small.
They are small. Absolutely. They're extremely small. That's going to be my next statement up here. As far as heavy, they're about 10,000 times lighter than a proton or a neutron. However, they are responsible, if you remember his little analogy of the fan, by moving around out there, they're responsible for filling up most of the volume of an atom. So they're very small mass, but take up most of an atom's space. They're responsible for most of the space of an atom, most of the volume. Because remember, he was doing that, and I've told you too, if I have a football field, all right, and the atom were the size of a football field, the nucleus would be the size of a pea. Most of that is empty space filled up by these really fast-moving electrons, which are weird guys. They're kind of like particles. They're kind of like waves. You're going to find that out when we talk about them in the quantum theory. And if you think you understand electrons, then you're smarter than me, because I don't. And I don't think many people do. It's very, very difficult to envision something that's both a wave and a particle, and is here and then he's there and it doesn't go in between. It's very strange, guys. We'll talk more about electrons in the future. However, for today, there's one term you need to know about electrons. What do we call a guy who has lost or gained electrons? He has a special name. Remember it from the past? You probably heard it.
Compound bond?
No, not a compound. That would be when we put two atoms together and make a compound. Think. No. You're back on the. You're going on the compound here. I'm talking about. It begins with an I.
Isotope.
It's either ion or isotope. I heard both of them, and that's what we often do. We often get them confused. A guy who's lost an electron or gained an electron is called an ion. Okay. They're often mixed up because they both. Like I said, there's a lot of things today. You're going to get atomic number. You're going to get mass number, and tomorrow you're going to get atomic mass. Atomic number, atomic mass. All of them are going to get confused. You're going to have to keep them straight in your head. And you know what? Because this is the difference between chemistry and other classes. My guess is you're having a hard time keeping them straight right now because in the past you just learned them for a chapter and then you never saw them again. You went right into your biology. You will be using the atomic numbers and mass numbers and the atomic masses for the rest of the year. I'm not exaggerating that. You'll be using the periodic table for the rest of the year. You have to know what those numbers mean. Okay? So they won't be as confusing as you go on. It's not like I have to memorize ion. No, you don't have to memorize these things. You'll be using them so much, they'll be familiar to you. An ion is a guy, it's a charged atom, who has lost or gained electrons. And he's got a charge to him. Like if you look at the periodic table up there, this is what carbon, it's a block in the periodic table, and it has 12.011. Don't draw this. It says carbon here. It's a big C and a 6. Okay? All those guys in the periodic table, every one of those things means something. We're going to have a whole chapter, by the way, just on the periodic table. But I'm going to tell you one thing this means for right away. Carbon, right here, that's 6. That tells you how many protons he has. Now, if carbon has 6 protons, and he's neutral, what do you think? How many electrons do you think carbon has? 6. Because you probably remember protons have a positive charge, right? So if I've got 6 positive charges, and if I have 6 negative charges, they're going to cancel each other out and it'll be neutral. If I were to take away one of those guys, if I were to remove an electron, just one electron from a carbon atom, what charge would he be? He'd be what? Take away an electron, he'd be what? Positive. Are you sure? Are you sure?
Positive.
You're positive. It's exactly right. You can see you're positive. Very good. That's right. You're positive. You gotta get with the program here. All right, good enough. So that's what an ion. An ion is a guy who's lost, or I could give him an electron. If I gave him an extra electron, what charge would he have? Negative. He'd be negatively charged, which kind of seems counterintuitive, because after all, I'm giving him more of something, but I'm making him negative. But remember, what I'm giving him has a negative charge. Electrons are negatively charged. All right, let's go on to protons. Okay, now what can we say about protons? Well, first of all, we can say that protons get paid because, after all, they're not amateurtons. They're protons. First way to tell them apart. Okay. But what charge do protons have, Jared?
Positive.
Are you sure?
Yes.
Are you sure?
I'm positive.
You're positive. Okay. Positively charged. Okay, protons are positively charged. They have a +1 charge. They balance out the negative charges of the electrons, so the atom's going to be neutral if it's a neutral atom. If it's not an ion. Where are those protons located? Allie. It's not really Allie, it's Ellie, but we'll call her Allie today. Your name is Allie today. Where are they located? Inside the nucleus, right. They're located in the nucleus. Who called you Allie today anyway? Emily.
So that surprise you?
No. Okay, so they're located inside the nucleus. These guys, if you remember, are about 10,000 times heavier than an electron. They are massive, much heavier compared to what? Compared to an electron. And they're located inside the nucleus. They have a large mass, but a very small volume. They take up about, like I said, the size of a pea if the atom were the size of a football field. So, you know, they're not very big, but they are heavy compared to an electron. Now, there's a special term that goes along with protons. Kind of like ions or atoms that have lost or gained electrons, there's a special term we know about protons. The number of protons in an atom will never change because it's actually called the atomic number. Number of protons in an atom is the atomic number. Every single element has its own individual, unique atomic number that will not change, or it's not that element anymore. Okay? It's different for every element. Okay, so we've talked about protons and electrons. What's left to talk about? Zach, what do you think?
Neutrons.
Neutrons. Okay? They're not ultrons, they're neutrons. They're Jimmy Neutron. Ever watch Jimmy Neutron? All right. I have a little cartoon for Jimmy Neutron when we do the nuke chapter. He flies across the board. It's not really that impressive, but it's like. What charge do you think Jimmy Neutrons have, Ronnie? Neutral. Absolutely. No charge. 0. And where are they located, those neutrons? What do you think, Zach?
In the nucleus.
They're in the nucleus. Neutrons, nucleus. It's kind of easy to remember. Neutral. Okay. They're very similar to protons. You're going to find this out actually when we do our nuke chapter, which is at the very end. They're almost identical to protons in mass and size. There's a small difference. Obviously, it has to do with the fact that they have a +1 charge. Protons do and neutrons don't. So they have a relatively large mass and small volume, very similar to a proton. What do we call guys, atoms, that have lost or gained have a different number of neutrons? What's the word we use for them? It's not ion, it's isotope. Yeah. Atoms of the same element with different numbers of neutrons in the nucleus. I'm going to draw my little carbon here. I like to use carbon early on, and he's right up there on the periodic table anyway. Let's talk about him after you copy that all down. Now, I told you already this number here was the atomic number, okay? And that is the number of protons. I also said the number of electrons for a neutral atom is going to be the same. So if I've got 6 protons, I've got 6 electrons. As far as the neutron is concerned, there you have a lot of choices, okay? Some atoms have 3, 4, 5 different types, 5 different isotopes of the same element. Let's talk about a couple of things here. Say I have the carbon atom, and he's sitting there, he's all happy, and he's all neutral. And I take an electron away from a carbon atom. Electron. What have I made if I take an electron away from carbon? What have I made? An ion. What charge would that ion have if I took an electron away?
Positive.
Okay, so a positive ion. What about if I take a neutron away from carbon? What would I have? What do I call him? An isotope. I'd have a carbon isotope. Or if I added the neutron, if I took away an electron, if I add an electron, I'd have an ion. Took away a neutron, added the neutron, I'd have an isotope. What if I took away a proton from carbon? What would I have? I would have boron. You stupid boron. Right? I'd have boron. Because boron's the next guy down the line, he's got 5 protons. And if I take away one, I've made a whole new atom. That actually does happen. I can add and take away. It happens in radioactive decay. It happens when we try to smash atoms together and get them to stick, make them heavier, make them lighter when they're decaying. So yeah, I can absolutely do that. All right, happens all the time in radioactive elements. But here's the key: take away an electron, got an ion. Take away a neutron, got an isotope. Take away a proton, I got somebody else completely. I don't have carbon anymore. I got a totally different element. Okay. All right. Good enough. Now, there's one more term here I've got to give you. It's one of those that's over there. It's often confused. Mass number versus atomic mass. I'm not going to have time today to talk about atomic mass, but we will talk about mass number today. Mass number doesn't fit under any one of these three because he kind of includes a couple of them. He is the number of protons plus the number of neutrons in an atom. We kind of need that to tell what atom we're talking about, what isotope specifically of an atom we're talking about. Because as I told you, many of these guys have multiple isotopes, many different versions of the same element. Carbon being a good example. Carbon is, you ever hear of carbon-14 dating? You ever hear that? That's how you tell how old something is. We're going to talk about that in the nuclear chapter as well. But for right now, all you got to know is carbon-14 is different from carbon-12. All right, I'm going to show you how in just a minute when I do an example of how we do the different notations. See, I'm going to need that mass number and the periodic table to tell what the notations of these guys, how to write the different isotopes. And let's learn how to do that right now. Atomic notations. We're going to do it 2 different ways. A nuclear symbol, and I'll do examples of that one first. But you know what I'm going to give you also right now, while you're writing that down? I'm going to pass around your periodic tables. You need these to do these. Although the one up there on the board, or on the wall, I should say, that guy is about half the periodic table. The other half, all of them are on here. How do we do nuclear symbols? Let me show you. What you'll do, and if you put this over to the side over here, okay? Don't write it till I'm done so you know how much room you'll leave. I guess I'm going to... If you're going to write, let's use black, easier to see. Don't write this yet. You have the symbol written, and as a superscript before it, you put the mass number. And as a subscript before it, you put the atomic number. Okay, so write that down. That's how you write a nuclear symbol. The mass number over the atomic number next to the symbol. And that probably doesn't mean a whole lot to you until I do an example, which I will right now. Example 1, we'll call it. And I'll use, like I told you, carbon-14. We're going to talk about, actually, before I write carbon, I want you to have a chart. I'm going to put the examples underneath here, and carbon-14 will be here. But I want you to tell me how many protons, neutrons, electrons, atomic number, and mass number of each of these guys. Okay? We'll do example 1 right there. So a little chart. Okay, and then for carbon, we're going to fill that chart in for carbon-14. Now that symbol gives you everything you need to know. Tells you everything you need to know to fill that chart in. For example, everybody looking up there? What is the 6 in 14 over 6? What is he? Use the atomic number. See, the atomic number is at the bottom, the mass number is at the top. So let's just fill those in right away. 6 is the atomic number. The mass number is 14. Everybody see that? If I give you this on the test, if I give you that on the worksheet you're going to do in a minute, you know the atomic number is 6, the mass number is 14. Now, how does that tell you everything else? Well, pretty easily. What does the atomic number mean? What does he mean? How many protons he has, right? So the protons are 6. What else has to be 6? Because I'm assuming it's a neutral atom. No. The electrons will have to be 6 because it's a neutral atom. Because 6 positive charges and 6 negative charges would balance out and be neutral. Now, how many neutrons must this guy have? Everybody see why it's 8? Protons plus neutrons equals the mass number, right? The mass number is 14. I've got 6 protons. How many neutrons do I have to have? See? 6 and 8 is 14. See it? Make sense? Guess what? I could do these backwards. I'm going to leave this blank, and I'm going to give you information out here. What if I told you a guy has 7 protons, and he has 6 neutrons? Can you fill the rest of that stuff in, including this? Yeah, if you have a periodic table. First of all, you may notice that some of these columns are going to be identical straight down the line. Right down the line for both of us. God bless you. All right, you ready? There were 6 protons and there were 6 electrons, and that's also the atomic number. That's going to be the case in every case. There are, whatever the number of protons is also going to be the number of electrons, assuming he's neutral. And it's also, of course, going to be the atomic number because that's the definition of atomic number, the number of protons. So those are always going to be the same. How do I get the mass number in this case? I'm not subtracting. I wasn't given the mass number. I'm going to add them. I'm 7 and 6, protons plus neutrons, because I'm given those this time, and I'll get 13. You see it? Right? 7 and 6 is 13. Now, finally, this is the hard part. I know it's going to be 13 over 7. I know that. But what's the symbol of the element? You can't tell without the periodic table. What element? How do I know which element I'm talking about? How do you know what element I'm talking about? The element whose protons or atomic number is 7. Because that never changes. Who has an atomic number of 7 on your periodic table? And so it's an N here. You cannot go by the number of neutrons. Doesn't mean anything to the identity of the element. Can't go by the mass number. Doesn't mean anything for the identity of the element. All that matters for an element's identity is the proton. That is the atomic number. It's the only thing that matters. What is a guy who has 52 electrons? What is he? I mean 52 protons. What is he? Tellurium. You don't have to know anything else about tellurium. You don't have to know how many neutrons he has. You don't have to know if he's an ion, if he's lost or gained electrons. You know if he has 52 protons, he is tellurium. You know silver always has 47. All right, now I'm going to do a second way to show you these symbols, just because you often see them written both ways. Okay, try this one with the hyphen notation. Hyphen notation is going to be a little less descriptive than the nuclear symbol. You'll just have the symbol and then the mass number. Symbol followed by the mass number. So, if I gave you O16, could you fill the rest, assuming this chart carries all the way down, could you fill the rest of this chart in? Go ahead and do that. Fill the rest of that chart in, knowing this is O16. You can't do it without the periodic table, because what do you first have to know about protons and atomic number? It's not given to you here, like it was up here. So you got to look it up. How many protons are going to be in oxygen 16? How will you know that? Look at the periodic table. How many protons are in oxygen 16? 8. Everybody see why it's 8? Because they found the atomic number was 8. It's right there. If 8's the atomic number, it's also the number of electrons. In this case, since the mass number is 16, I can write that down right over here. It tells me the mass number. In this case, how many neutrons do you have? Don't be surprised. That can happen. It doesn't always happen. Don't assume every time these are going to be the same. But I did want to do at least one where they were. All right. Last example. let's say I've got a guy with 12 electrons and 10 neutrons. Fill the rest of that in, and we'll be done. Again, if he's neutral and he has 12 electrons, how many protons does he have? 12. If he's got 12 protons, that's the definition of an atomic number. He's got an atomic number of 12. If he has 12 protons and 10 neutrons, what is his mass number? 22. Add them together. Got it? And his symbol, I got three numbers up here, 12, 10, and 22. Which one actually tells me the identity of the element? The number of protons, or the atomic number, which is 12. And if you look at the periodic table, that is magnesium. Magnesium dash 12, right? No. Very common mistake. Yeah, it's followed not by the atomic number, but by the mass number. A lot of people do that. They put Mg 12 or O8. It's not. This is not the atomic number. It's the mass number. Okay. All right. Well, we'll get started on our worksheets now.